Hello, and today we're going to look at counting and probability. So, most of what we're going to look at today is all the different ways of counting things depending on the conditions that we have. So, for example, if we were to look at a social security number, this is a 9-digit number in the form of 3 digits, then 2 digits, and then 4 digits. So, theoretically, the idea is if we had 10 numbers for the first digit, 10 numbers for the second digit, and so on, we can end up actually multiplying all of these tens together to get 10 to the ninth power, which is 1 billion. So there are, in general, 1 billion unique social security numbers. Now, of course, this is not excluding some obvious numbers like having all of them being zeros or ones or whatever, as I highly doubt that these are, in fact, actual social security numbers that are allowed. But we've talked about this multiplication rule before, clear back in the first chapter of chapter 7, where we looked at just having a certain number of choices for the first item and the second item, and we could just multiply them together. So if we look at this next example of how many 6-character passwords can be made using just lowercase letters, well, if we have 6 different characters, first one has 26 choices, and same with the second, third, fourth, fifth, and sixth. So multiplying all of those together, and we end up with 26 to the 6th power. And surprisingly, this does actually give us a large number of 308 million. Now, of course, this is still including having all the letters being the same, so we could have all of them being A's or all of them being Z's or so forth. But what if we try and make this so we can combine more things? So what if we include lowercase, uppercase, numerals, and 3 special characters? Well, lowercase, that's 26 possible values. We have another 26 that are uppercase. There are 10 numerals, 0 through 9. And then we have 3 more. So in total, there are 65 possible choices per character in the password. And at the still 6-character password, this would be 65 to the 6th power. So the reason why there's so many different passwords that are possible is to prevent someone from stealing your password. So in that last slide, we were looking at how to count things with repetition, meaning we can have a character show up multiple times in a password. However, we can have what's called a permutation. Now, when we're looking at permutations and combinations, which I'll get into both those in a moment, we are going to start counting things that cannot be repeated, meaning all of these items that we're selecting are in fact unique. So let's suppose you have one homework assignment for each of your 4 classes: math, history, English, and psychology. All 4 of these assignments are due tomorrow, and you're trying to decide the order in which you will do your homework. How many different ways can you complete all 4 assignments? Maybe, for example, we want to do this in the order listed. So maybe we want math first, then history, then English, and then psychology. Or maybe we want math, then history, and then switch the last 2. So this would be a different way or a different order of completing these homework assignments one at a time. So if we were to count how many ways we can do this, what I'm going to do is I'm going to basically just have these placeholders to determine how many choices we have for each category. So I'm going to think of this first one as being the first homework that we do, then our second, then our third, and then our 4th homework assignment. So how many choices do I have for the first homework assignment? Well, I have 4 different subjects that have homework. So I have 4 different choices for that first assignment that you work on. Now, after you complete that first assignment, so after you complete math, how many choices do we have left for the second course or for the second homework? And it turns out there's only 3 of them left. So let's say that we do history next. That means that there's 2 choices left for the third, and then finally 1 choice left for the 4th assignment that you do. And it turns out that we end up just multiplying these together, similar to what we did earlier, except the numbers are um, decreasing by 1 essentially. So 4 times 3 is 12, times 2 is 24 possible ways. So now we're going to change things a little bit. Let's say that you do math first. How many different ways can you do the remainder of those assignments? Well, similar to the last case, we have 3 choices for the next assignment that we do, then 2 for the one after that, and then finally we have one last choice, which gives us only 6 possible ways of rearranging the remainder 3 assignments. Now, both of these examples are examples of a permutation, but we never really went over what a permutation actually is. So we are dealing with the permutation when we have the 3 following conditions. The first condition, all selections come from a single group of items. Then we have no item may be selected more than once. So basically every item is unique. The third condition, and this is probably the most important one because it's the main thing that keeps a permutation different from a combination, and that is that the order of arrangements matters. So arranging them in ABC is different than if I was to arrange it as BAC. We can kind of think of this as if we were to rearrange the letters, they would actually make different words. So one of the formulas we have for a permutation is the following. If every item in the group is selected, so in the last example, if we were to select all 4 homeworks, we can write that as 4, and then we use this symbol, which some of you may know as an exclamation point, but in this class we're going to actually say that this is a factorial. So all 4 factorial means is that we're taking 4 times 3 times 2 times 1, and that's the number of ways of arranging all 4 items in some particular order. So suppose there are 5 people in a race, and we want to figure out how many ways can those 5 people finish in different places. Now, we are going to exclude any kind of ties that they can have in any of those positions. So assuming that we have a definitive first, second, third, fourth, and fifth place winner, how many ways can we arrange those 5 people? Well, there are 5 people and we're selecting all of them. So 5 factorial is 5 times 4 times 3 times 2 times 1. And I believe this gives us 120. For fun, let's go ahead and look at 6 factorial. 6 factorial, of course, is just 6 times 5 times 4 times 3 times 2 times 1. And you probably noticed that, well, we already know what this part is. This is simply 5 factorial, or 120. So we can actually rewrite 6 factorial as 6 times 5 factorial, or we can rewrite this as 6 times 120, which will give us 720. So what is 7 factorial? We can take 7 times 6 times 5 times 4 times 3 times 2 times 1, and we end up with 5,040. Before I get too carried away, I do want to show you how to do this on your calculator. So everyone's calculator may be a little bit different, especially for those of you that have a scientific calculator. You may actually have to look for a slightly different button than what I'm going to look for. You'll actually want to look for a button that says PRB or PROB, and this just stands for probability. In my case, I want to find the 7 factorial, so I need to type in 7 first. Then, on a TI-83 and TI-84 calculator, I'm going to click on Math. I'm going to make sure I move my cursor over to PROB in my case. And then I select the factorial sign. So after selecting that, it should just show up as 7 factorial. I hit enter, and it gives me 5,040. Now, of course, I can go ahead and take 7 factorial and divide it by 6 factorial. Sometimes you may need parentheses around this bottom part. I'll just do that here just to be safe. And again, this will depend on your calculator as to whether or not you need the parentheses there. Now, this seems weird that we'd have 7 factorial divided by 6 factorial equals 7. So why is that? Well, if we use the trick that I had earlier for splitting up the 6 factorial as 6 times 5, we can see that if I do the same thing with 7 factorial, I have 7 times 6 factorial. So if I'm dividing both by 6 factorial, the 6 factorials cancel. This gives me with nothing else except for 7 in the numerator, and I guess technically 1 in the denominator, so 7 divided by 1 is just 7. So that is why I have that as my answer. Now, a little bit of a warning though. What if I was to try and figure out what 123 factorial divided by 121 factorial is? So let's just go ahead and plug this into my calculator. And I think it's okay to not use the parentheses in my denominator. Oh no, we end up with an error. Now, you might be freaking out because the calculator can't solve this relatively easy problem. So you might be wondering, what is this overflow error? What the calculator is doing in this case is it's actually trying to calculate 123 factorial first, and then it's trying to calculate 121 factorial and then divide both of those. The problem is that, if you probably haven't noticed, the larger the number is inside the factorial, the more it grows faster. And it grows so fast that I actually don't know exactly where the cutoff is on the calculator, but essentially 123 factorial has way more digits to it than what the calculator can even handle. Long story short, this number, 123 factorial, is simply too big for the calculator to handle. Now, I believe an iPhone can actually do this, and there's probably some other calculators that can actually simplify this. However, we don't really need those. All we really need to do is just do the same trick as before, take 123 times 122, and you basically keep going down until you realize that you can get the number to match with 121 factorial. And in this case, the 121 factorials will cancel, so we can go ahead and multiply 123 times 122 and get 15,006. And that is how you are now smarter than a calculator. So I don't have this in the PowerPoint, but I do want to bring up a couple more points here. Or rather, I want to look at just a couple more simpler examples than what we have up here. First one I want to look at is, what is 1 factorial? Well, 1 factorial is just, well, 1. Okay, simple enough. What is 0 factorial? Well, you might think, well, you'd start with 0 and then multiply up to 1. However, this actually is not equal to 0. In fact, this might seem really strange, but 0 factorial is actually equal to 1. Now, hold on, how is this actually equal to 1? Let's look at a little trick that we've been using and see if we can figure out what 0 factorial is using that trick. Well, according to what we've been looking at before, when we did 6 factorial as 6 times 5 factorial, the idea is that this trick, we would take that number times the factorial of 1 less than that number, right? So what if I was to rewrite 1 factorial as 1 times 0 factorial? Well, we know that 1 factorial was equal to 1. I think everyone is okay with that. And 1 times 0 factorial, well, 1 times anything is just that anything. So what we basically have is that 1 must equal 0 factorial. All right, so we know how to count how many ways to arrange all items, but what if we don't want to select all items to be arranged? So this can be a little bit tricky here. And maybe let's actually just look at this first example. So before we get into the formula, let's say that we have 10 flavors of ice cream, and we only want to pick 2 of them for our ice cream cone. Since the order in which I put the scoops of ice cream into my cone totally matters because, it's totally different ice cream if you taste strawberry first and then chocolate versus chocolate first and then strawberry, right? The chocolate just takes over the flavor and it's not the same. So, anyways, how many different ways can I stack ice cream into my ice cream cone? Well, we have, I guess if I was to try and draw my ice cream here. So I guess the two flavors in this case are probably like, I don't know, black licorice and strawberry. Interesting combination. For the top scoop, I would say that there are 10 choices for that, which means that since I cannot pick the same flavor for both the top and the bottom, that means that I would have to have 9 choices for the second scoop. So it's as simple as just taking 10 times 9 to get 90. Now, this may be pretty simple since we only selected 2 different items, but once we start selecting like 10 different items to be arranged out of, let's say, 100, this method may not be as practical. So that's where this formula comes into play. This formula actually takes all this work and puts it into a really nice formula to use. And essentially, what it does is it takes the number of ways to arrange all n items and divides it by the number of ways to arrange the non-selected items. And by dividing the number of ways to arrange the non-selected items, we end up actually having the number of items that we are selecting left over. So again, n is the total number of items that we have to select from, but we are only actually selecting r of those items. Looking at another permutation example, let's say a city has 12 candidates running for 3 leadership positions. The person with the most votes will become the mayor, the person with the second most votes will become the deputy mayor, and then the third place will end up being the treasurer. So how many different outcomes are possible for those 3 leadership positions? Well, we could do the same thing as what we had at the beginning of the last slide, where we take the 12 choices for the first position, times 11 for the second, times 10 for the third, and that would give me my answer. However, if I use the formula, I'd actually write it as follows. I'd have 12 permute 3. That's how we say that we have 12 things to select from, and we're only selecting 3 of them in a permutation. So 12 permute 3, using the formula, I would take 12 factorial divided by 12 minus 3 factorial. So this tells me I have 12 total items I can arrange, but I'm going to ignore the 8 items. But I'm going to ignore the 9 items that I did not select. So if I write 12 factorial as 12 times 11 times 10, then times 9 factorial to match up with the denominator, that would mean that the 9 factorials will cancel, and I'm left with basically what I had earlier of 12 times 11 times 10, which is 1,320. Now you may be thinking that this again may be more work than just the first method that I used. However, I can show you one more thing, and that is how to do this on the calculator. Now again, everyone's calculator is going to be different, but the way that you do this on at least a TID3 and TID4 calculator is as follows. First, you're going to type in the first number, so you're going to type in 12. Then you're going to find where PROB is on your calculator. And then from there, you're going to select NPR. So I have the first number, 12, and then it has a P, and then it wants me to type in the last number, which is 3. And sure enough, it gives me the same answer. Now let's look at what a combination is. Now notice that these first 2 criteria that we have are the exact same as what we had for permutation. So again, all items come from a single group of items, and we have unique items, or no item may be used more than once. The thing that makes this different is that the order does matter. So we would treat ABC as the same thing as CAB. So in this formula, we're basically having to divide by an extra r factorial. Now, what is this r factorial? This is simply just the way of arranging those items that are selected. And the reason we're trying to divide by this is because we do not want to count all of those ways of arranging those items. So in this case, since we have 3 items selected, we would be dividing by 3 factorial, or 6 arrangements. So even though there are 6 ways to arrange those 3 letters, we only want to count it once and not 6 times. That's why we end up dividing by 6. So now let's look at some examples of how to use a combination. So now let's suppose I have a bowl of ice cream, and out of the 10 choices of ice cream, I only want to select 2 different flavors in my bowl. Now, of course, because of how a bowl is arranged, notice that with their scoops of ice cream, they're going to end up being side by side. So in this case, it doesn't really matter if the strawberry ice cream is on the left or if it's on the right side of the bowl, as you can just simply flip the bowl around and you basically have the same ice cream. So it doesn't really matter in which way the 2 scoops of ice cream are put into the bowl, they're going to be side by side and not stacked. So in this case, what we have is we're going to have 10 choose 2. So we're going to have 10 factorial divided by 10 minus 2 factorial times, and then we have 2 factorial, because that's the number of ways of arranging those 2 items. Now, if you're going to just type this fraction into your calculator, you will want parentheses, or an extra set of parentheses on that denominator. Doing this by hand, we end up with 10 times 9 times 8 factorial. And we divide this by, well, 10 minus 2 is 8 factorial. And then 2 factorial is simply just 2. 8 factorials cancel. I can cancel a 2 out with the 10. So we end up with 5 times 9, which is 45 unique bowls of ice cream. Again, on the calculator, I would type 10 first. Then I go to, in this case, math, then PROB. Then I select NCR. I would type in the number 2 in this case. Enter, and I get the same answer. With the poker hands, we're trying to figure out how many different 5-card poker hands can be dealt from a standard deck of 52 cards. In poker, I should probably mention that the order does not matter in how you get the 5 cards in your hand, as you can simply just rearrange them so that you can see clearly what kind of hand you have. So because the order does not matter, this will end up being 52 choose 5. Now, because of how large these numbers end up being, I'm going to go ahead and just type this one into my calculator. So I'm going to type in 52 combination, or 52 choose, and then we want 5 cards out of the 52. So it's about 2.5 million unique hands in a poker game. So the answer ends up being about 2.5 million. Now, for the second part of the question, it's asking what is the probability of getting a royal flush? Now, royal flush is where we get a 10, jack, queen, king, and ace, but they are all in the same suit. So first we need to figure out how many royal flushes there are. Well, it ends up being that there are only 4 possible royal flushes, basically just one for each suit. If we take the number of royal flushes and divide it by all of the hands possible, we'll end up with our probability. And notice that in this case, it's a really small probability of 1.539 times 10 to the negative 6th power. If we wrote this as a percentage, this is about 0.00015%. Well, that's all I have for this, so thank you for watching.